Hello and welcome everyone to tonight's public talk. In just a moment, I'm going to be joined on this virtual stage by Dr. Angela Speck. She is the chair of physics astronomy at the University of Texas San Antonio campus. And it is my pleasure to once again get to be part of the American Astronomical Society's Eclipse task force with her, which she is one of the chairs of. I think she is single-handedly, as a force of nature, making Eclipse organization happen through public talks all across the United States, and it is a great honor to get to have her here on my virtual platform. So without further ado, here is Angela. Thank you.
Thanks, Pamela, and hello, everybody. So I'm going to be talking to you about the next two solar eclipses that are going to happen in the United States. And so during this talk, I'm going to talk about why eclipses happen, and then some details about them and what you can expect to see, and then a little bit about the specific eclipses that are going to happen, one in 18 months in October 2023, and one exactly 2 years from today. But let's start by talking about why eclipses happen. So we get an eclipse when the moon comes between us and the sun. So in this slide, you can see, oh, maybe you can't see. There we go. In this slide, you can see the moon is between us and the sun. And if you're standing on the right bit of the earth, you will not be able to see the sun at all. That is why we get eclipses. But I want to get into this in some detail. So if we look at how the moon changes over the course of a month, what we see is, and here I've got this calendar for 2022 of the moon phases. So we know that the moon can be a skinny crescent up to a full moon and then back to a skinny crescent. And every month it goes through those different sizes. And you can see here that we've got new moon, which is when we can't actually see the moon at all, skinny crescent getting bigger and bigger up to half full, and then getting bigger and bigger up to a full moon, and then getting smaller and smaller and smaller again. We can also see that every month there's a full moon and every month there's a new moon. And we need to understand these phases of the moon to understand when the moon gets between us and the sun and how often that happens. So when we talk about the phases of the moon and what happens, we have to think about the moon orbiting the Earth. Here I've got a nice view graph of the Earth in the center and the moon orbiting the Earth. It's actually just one moon going round, shown 8 times. There aren't 8 moons orbiting the Earth. And if we look at the moon directly to the right of the Earth, what we can see is the moon is half lit up by the sun, which is way off to the right of the screen. And the sunlight's coming in and it's lighting up one half of the moon. But that half that's lit up is pointing away from the Earth, so we can't see it. And that is what the new moon is, when we cannot see the moon at all. But the moon is orbiting the Earth. And so a few days later, it's got to the position just around, following a counterclockwise direction. We've got to the waxing crescent. And this is where still half the moon is lit up, but now we're seeing a small portion of it as seen from the Earth. And so what we can see is just this tiny crescent of the moon. But the moon is going to keep moving around the Earth. And so now it's still only half lit up, but now we can see half of that side and half the dark side. So it looks like it's half full. But the moon keeps moving. And as it gets bigger and bigger, we can see more and more of the lit up side until it gets all the way around to the other side of the Earth. And so now we've got the sunlight hitting the same side of the moon, but that lit up side is now all pointing towards the Earth. And so the people on the night side of the Earth can see the full moon, but the moon's going to keep moving. And so now we're going to see less and less and less of it until we get all the way back to new moon. And it takes about a month. In fact, the word month comes from moon. It takes about a month to go from new moon through all of the phases and back to new moon. Now we can see from this that it looks like the moon gets between us and the sun at new moon. But if that was the case, why don't we have an eclipse every month. Well, the problem is we're thinking about this two-dimensionally. I like to remember there's a line in one of my favorite movies, Star Trek: The Wrath of Khan, the original Star Trek II movie, where they're talking about Khan's way of thinking, and it's two-dimensional. And actually, a lot of us tend to think like that. But to understand why we don't get an eclipse every month, we have to think about things in 3 dimensions. So I want you to be, if you're looking at my face, we're going to pretend that my audience is the sun and my face is the earth, and here's the moon coming in the way. And if it gets right in the way, you get an eclipse. You can no longer see my nose. That must be an eclipse. But actually, most of the time, the moon is down here, just below my chin, or up here. It is not directly in the way. So it's in the direction towards the sun, but not directly in the way. To show this schematically, I want you to see the next slide. And so what we have is, here again, I've got the Earth. The sun is still way off to it's actually the upper right. And the plane in which the Earth exists and the sun exist is marked here. And then it also shows you the plane that the moon is moving around the Earth. And so you can see, if you look at the moon right above where it says 5 degrees, the moon is so high up above where the Earth is that even though one half is lit up and the other half is in darkness, the dark side point is on the side towards the Earth, but the shadow will not hit the Earth because it's too high up. Likewise, if we look at the moon down at the very bottom left, that is too low down. It's not hiding in the Earth's shadow, so we don't get a lunar eclipse either. And this is what it's like most of the time. You don't get a proper alignment. The moon at new moon is always in the direction towards the sun, but it might not be directly lined up. It might be just above or just below, but not right in between. So when do we get it in between? Well, here you can see it's that same diagram, but now the Earth has moved around the sun. So the sun now appears to be coming from that upper left position. And so at this point, now the moon is at that point where it's in the same plane as the Earth and the sun. It is exactly lined up. And so now we're going to get a solar eclipse. The shadow of the moon is going to hit the Earth. Likewise, if we look at the other side, you can barely see it. There is a moon hiding in the shadow of the Earth, and we'll get a lunar eclipse. So we don't get an eclipse every month because it just doesn't line up properly. Even though the moon is going around the Earth and going in the direction towards the sun every month, it's not always exactly lined up. To kind of summarize this idea, what we can see here is most of the time the moon is too high or too low, and so we don't get the shadow hitting the Earth, and that's what's going to happen most months. It's also going to explain why we can see the full moon. The sun's light now coming from the left is hitting the moon and then bouncing back to the night side of the Earth, so we see the full moon. But just occasionally, and I'll talk about how occasionally in a minute, we have the full moon directly between us and the sun, and so you can see that the shadow of the moon hits the Earth and we get an eclipse. Likewise, the moon falls in the shadow of the Earth and we get a lunar eclipse. Now this view graph also shows why you're much more likely to have seen a lunar eclipse. They actually happen at about the same frequency. There's about as many lunar eclipses as there are solar eclipses, but everybody on the night side of Earth can see this lunar eclipse. And so this is a much more common thing to see. It doesn't happen more often on a global scale, but the whole of one side of the planet gets to see it. On the other hand, if we look at the moon shadow, only a tiny bit of the planet is in eclipse. And in fact, sometimes it eclipses so that you only get a partial anywhere on the planet. And sometimes we get another sort of eclipse, which I'm going to get into in a second. So not all of them are total, but even when we do get totals, it's a tiny portion of the Earth. Okay, so now let's put everything together. Here I've got a complicated diagram, but I'm going to talk through it. We've got the sun in the middle. We've got a nice blue Earth here going around the sun, and we've got a moon going around the Earth at each position. Now you can see that there's that 5-degree angle between the moon and the Earth. If you look at the moon to the upper left, you'll see that it marks on the 5-degree angle. So if we consider that position there, we can see that actually the moon is lined up and we're going to get an eclipse. The shadow hits the Earth. But as the Earth moves around the sun, now the moon isn't going to be in alignment anymore. And this is shown really well in this lower left position, where the new moon is so high up that the shadow is not hitting the Earth at all. But the Earth's going to keep moving. And so about another 3 months later, we're back to having the moon lined up again, and we're going to get an eclipse again. But the Earth's going to keep moving, so it's going to be out of alignment again, all the way around to the other side again. And so we can see here, we get an alignment of the sun, moon, Earth at one side of the orbit and at the other side of the orbit, but not in between. So that means twice in an orbit. So that's twice a year. So we actually get eclipses, both lunar and solar, about twice a year, but they are not necessarily all total solar eclipses. So this is one of the reasons why they're much less commonly seen, though, is that although they happen with the same frequency, you're not going to be in the right bit of the planet all the time to see the solar eclipse. Okay, so let's just bring that all together. And just to remind you, we get an eclipse when the moon comes between the Earth and the sun, but that looks like it should happen once a month every time the moon goes around, but it doesn't because of the angle of the orbit of the moon. And so we actually only get the alignment about twice a year, and not all of those alignments will be total solar eclipses. Now, let's think about what's happening in the system, because so far I've been showing this and it's all very static, but everything's moving, right? The Earth is moving around the sun. So here I have the Earth on its orbit, that's the blue line, and it's moving in orbit around the sun. The moon is moving around the Earth. And so we have this green orbit shows the moon moving around the Earth. And so if you want to be standing where you cannot see the sun at all, you have to be on the tiny little dark spot that you can see. If you're in the slightly lighter color, but still shaded, then you'll get to see a partial eclipse. If you're standing there and looking towards the sun, the moon is blocking out part of the sun, but not all of it. Only on that very dark spot, in this case in West Africa, can you see a total eclipse. But everything is moving. So as the moon moves along its orbit, and the sun and the Earth moves along its orbit, and the Earth is spinning, it might be the spot is in this position for this moment, but a moment later, it's going to have moved across the ground a little bit. And so actually the place you can see an eclipse from draws out a path across the ground, and in fact, across the ocean too. And it takes a couple of hours or 3 hours for the solar eclipse to happen. And over that time, it draws out a path a few thousand miles long. So let's have a look at that. Here I'm showing you this is showing you all of the solar eclipses, total solar eclipses that have happened in the last 10 years and for the next 40. This is a 50-year map of eclipses. Each of these is just where you need to be to see a total solar eclipse. And there's a couple of things I want you to take away from this. One is, first of all, most of the planet is ocean. And so the chances are you're more likely to see it on the ocean than elsewhere. The other thing I want you to take away from this is most of the planet does not get to see a total eclipse in a 50-year period. So even though they happen approximately every 18 months, once you account for the other types of eclipses, which I'll come back to, you get total eclipses about every 18 months on average. But the chances of it being your bit of the planet are very slim. The area of each of these little pathways is only about 1,000th of the Earth's surface area. So you have to be on that 1,000th of the Earth to be able to see it. Okay, so I've talked about why they're rare and how small of an area of the Earth gets to see it. But let's talk for a few minutes about what you should expect to see. So during a solar eclipse, it's not just what you see, it's what you experience. Let's start with the partial phase. So before and after the eclipse, as the moon is moving into place, you're going to see the moon start to take bigger and bigger bites out of the sun. As you're looking towards the sun, safely, which I'll come back to later, you're going to see the sun get smaller and smaller and smaller. And then you'll get a total eclipse. And then the moon continues to move. And so you'll see more and more of the sun until it's completely out of alignment again. But what do you experience during that time? Well, first of all, as I said, you need to view it safely. You need to have some way of looking at the eclipses safely. I'll come back to some other ways of doing it, but one of the easiest ways is to get these solar viewing glasses. You can actually use them to look at the sun anytime, not just during eclipses, and they keep your eyes completely safe. And I'll talk about them a little more as I go along. But what do you see during a total solar eclipse? What do you experience? Well, first of all, for the first 75% of it, unless you're actually paying attention with the glasses or some other ways of looking at it, you're not even going to notice. The brightness doesn't change that much. So you don't really notice until it's at least 75% eclipsed. But at that point, you're going to start to see and experience some other things. First of all, I want you to look at the image in the bottom right. What you're seeing here is the view under a tree. I want you to imagine what it looks like under a tree, just on a normal day. And you don't get nice crisp images of like the gaps between the leaves. It looks kind of dappled and messy. And it's because what happens as the light comes through the gap in the trees, you're going to get, it behaves like an aperture. That is to say, what happens is it's going to make an image of the sun, but normally the sun is just round. And so what you get is lots of little round spots on the ground. And that's why when you look under a tree, you don't see a nice simple image of the ground, of the gaps between the leaves. You see something that's kind of dappled and messy. But as you're eclipsing, as the moon is eclipsing the sun, now you're going to get to see it as a crescent, because that's the shape that the sun has now. And so as the light is passing through those gaps between the trees, the leaves, you're going to get to see these crescents. And that's what you can see in this image here. It's pretty awesome, right? The other thing is that animals will react. Particularly birds are notorious for this. Think about whether you live in a city or out in the country, you'll have seen birds do this thing, usually after sunsets, but before it's gotten dark. Some birds will do this swarming thing where they swarm around a lot and they're flying around in their little flock things. And then when it gets dark, they all land and go to sleep. They're often quite noisy when they're doing their flocking thing, but then when they land, it goes quiet. So in that run up, as it's getting darker and darker in the last part of the partial eclipse, it's not complete, the sun is not completely eclipsed yet, but it is getting darker, and it feels kind of like after sunset in terms of the colors of the sky. Now, it's going to be, the birds are going to be making all this noise and flying around a lot. Other animals are going to do things like cows will start moving back to the barn because they think it's bedtime. And dogs might start barking if that's what they normally do. And there are some other animal effects that I'll come back to. So even before we get to the total eclipse, you're going to experience some other really interesting things. Here is another view of that idea that I was talking about with the leaves. So here what you're seeing is this white card. They've just used a hole punch like you would use for a ring binder to make the words eclipse May 2012. This is the last time there was an annular eclipse in the US. I'll talk about what that means in a second. If you look closely, and I'll give you a close-up in a minute, you can see that the projected image doesn't have circles. It has the little crescents, and so you're seeing a partial eclipse, and it's shown in the way it spells out the words eclipse May 2012. And so this is another way that you can look at the partial phase and not need to have special glasses or anything like that. So that's not the only way you can do that. In fact, anything that makes little holes is going to work. You can see here, that's a close-up on that image we were just looking at, but on the right, that's a colander. Think about what, a thing that you drain pasta in, or vegetables, whatever you use it for. And what you can see here is during the solar eclipse, instead of having little circles projected on the ground, you have little crescents. So anything that can make little holes for the light to pass through is a way that you can then make a projection on the ground. And it makes for some fun things as you're waiting for the main event. In fact, you can even use your hands. Here you can see an image of a guy wearing lovely sandals. You can see him crossing his fingers so that he's making small gaps. So he's basically got his fingers crossed kind of like this. He's making small gaps. And then you can see the image of small crescent suns on the ground where it is projected through those gaps. So there's lots of ways that you can have fun and enjoy the partial phase as you're waiting for the moon to move all the way in the way. Now, I said that animals do some interesting things. As we're getting towards the eclipse, there's some other things that happen. Plants and other animals will also react. So for instance, the sedge in Wyoming behaved differently during the 2017 eclipse. And this other image that you can see that's got a picture of a bee on a thistle, at least I think it's a thistle. In fact, this study was done during the 2017 eclipse, and they showed that bees stop buzzing. There's all sorts of issues of insects, things like cicadas may stop making noise and so on. And so there's all sorts of effects. If you've got things like mimosas that will close up during nighttime, then they will start to close up once it's getting dark. And so there's all sorts of effects that are going to happen as we're heading into darkness. Okay. Now, let's go back to some of the visual stuff. One of the coolest things that you get to see just towards the beginning of the total phase, end of the partial phase, is what's called Bailey's beads. And what I want you to see here is we're looking at the moon is moving in the way. There's just a tiny sliver of the sun left to see. And we see these little bumps and wiggles. And what we're seeing here is the topography of the moon. That is to say, the moon is not a smooth orb. It's not perfectly smooth. It has mountains, it has craters. And what you're actually seeing is mountains and valleys. And so where you can still see sunlight, that means that there is a valley that is letting sunlight through, and the mountains where they are, it's blocking more sunlight. And so we're going to take a close-up on this, and we're going to see. And if we look at this, if we look at the one on the far left, there's quite a bit of the sun left to be blocked out. But as we move to the next one over to the right, you can see you're starting to see the bumps and wiggles. And this is where we're starting to really block out the whole of the sun. And what's left for us to see is just the bits that can come through the valleys. And in fact, if we go all the way over to the far right, you can see there's just a couple of valleys left. This isn't actually the last thing that you see. The last thing that you see before you go into the total eclipse is what's called the diamond ring. So what you're seeing here is this white stuff that you can see around the edge. That's the extended atmosphere of the sun. It's called the corona. It has nothing to do with the beer or the coronavirus, thankfully. But this is always there. This isn't something that suddenly appears because there's an eclipse. It's always there. But, when it's very, very bright, it's hard to see something. Think about, a bonfire at night versus a bonfire during the day. You might not even notice it during the day, but at night, it's really, really obvious. Well, this is something that most of the time the sun is so bright that we cannot perceive this atmosphere. But once the sun is blocked out, it starts to show up. Now, we don't see it until this point. At this point, we've blocked out enough that you can actually start to see it all the way around. So you see a ring of white around the moon, but there's still one valley that's letting light through, and that is the diamond. That is the bright part on the left-hand side. And that is the last thing you see as the moon is moving into place. It's also the first thing you see at the end of the total eclipse, as the deepest valley on that side will let in light too. So this is where all of this happens before you get to totality. And then the moon is completely blocking out the sun. And what you get to see looks something like this. Now, this is an image that was taken by Rick Feinberg, who recently retired from the American Astronomical Society. He took this image in Madras, Oregon in 2017. I guarantee that this is really what it looks like. This is what it looked like where I was in Missouri. And what you can see here, this is that white stuff we were looking at before. This is the corona. It's the extended atmosphere of the sun. And it really does look like this. And this extends quite a long way. You can also see here what looks like a star. It really gets dark enough. It's going to be dark, like it could be as dark as a full moon night. So the corona here is about as bright as the full moon. but it might be not quite that dark, and I'll come back to that in a little while. You can also see there's a little bit of pink stuff just off sticking up here. Have you ever seen images of the sun that are from, say, NASA or other probes, where you've got these big, beautiful loops of gas that's coming off the surface of the sun? That's basically what you're seeing here. It really is this pink color. And this is something that you don't even need binoculars or anything, although you could look at this through binoculars completely safely. Remember, I said it's only as bright as the full moon. But this you could see just naked eye. Okay, I was wearing contact lenses, but I could see it without using any extra visual aids to be able to see it. And so you can really see all of this. But at the same time, it's getting dark like a full moon night. So you should expect to see some planets. Planets are pretty bright. Remember, Venus and Jupiter tend to be brighter than any of the stars. And then if it's dark enough, you'll also see some stars. And so all of this is popping up all at the same time. But that's not all that's happening. You just blocked out the sun. I want you to imagine what it's like when just a cloud comes in front of the sun. It's a hot summer's day, a cloud comes in front of the sun, and it gets cooler. But now you blocked out the sun above the atmosphere. It actually can get up to 10 degrees cooler. Depends on the humidity, but it can get up to 10 degrees cooler. And you really feel that. You feel that coolness. You're also going to get some breezes. This has to do with the change in temperature. That change in temperature causes change in air pressure, which gives rise to some breezes. And so what you will feel is these lovely cool breezes on your skin. So it's not just something that you're watching, you're also listening out for the animal noises. And remember, I said the birds, they do that flocking thing, but then they'll all go quiet. But if you're with lots of other people, there'll be lots of screaming of all these people going, oh, it's so gorgeous. And, you know, possibly not as high pitched as that. And so you're hearing it, you're feeling it on your skin, you're seeing it. It's an amazing experience. At the same time, the eclipse itself and the stars and the planets are not the only thing to look out for. What you can also see is this beautiful sunset color around the whole horizon. So I want you to imagine that you're looking towards the sunset. The sun's already set, and you've got the sunset colors on the western horizon. If you look to the eastern horizon, it's going to look dark already. Well, now what you have is, it's like that, but now the dark is up where the eclipse is, and it gets lighter as you move away from the eclipse. It has to do with the light scattering in the atmosphere. And as you get down to the horizon, that's where you're getting the sunset colors, and it goes all the way around the horizon. So if you can find a place to watch it that gives you that full panoramic view, you actually get to see something that you won't get to see in any other environment. Okay, so all of these things are happening, and yet you may only have a few minutes to experience it. So you have maybe 90 minutes of partial phase, and then depending on where you are, you may have anywhere from, you know, a few seconds to a few minutes to experience looking at the corona and the dark black moon and the little pink bits and the stars and the planets, and feel the wind and look for the horizon and listen out for what noises are around you. And all of these things are happening all at once, and then it's over. It is an incredible experience and totally worth it. And it really doesn't last very long. Okay, so I just talked a lot about total eclipses, but the next eclipse that's going to happen in the US is actually an annular eclipse. So I want to talk about that and why they happen. And here you can see an image of annular eclipses. And again, you're going to go through, this is basically showing you a time lapse of what happens with the moon is moving in front of the sun, and it's taking out more and more of a bite until it's directly in between. But you can still see the edge of the sun here. And so as the moon is moving out of the way again, we get back to a partial phase. This is called an annular eclipse because the word annulus is just a fancy word for donut. And you have this ring or donut of light that you can see around the edge. Sometimes it's called the ring of fire. Now, I don't know that I said it explicitly, but during the total eclipse, you do not need to have any eye protection. It is completely safe. I said it's as bright as the full moon. But during the partial phase, and if it's an annular eclipse, all the time, you must not look at it directly without something protecting your eyes. I want you to think about it like this. The sun is about 1 million times brighter than the full moon. So think about how bright the full moon is to look at. Now, that means that if you've blocked out only 90%, and let's face it, there may be 10% still showing in this image. If you've only blocked out 90%, then you've still got 100,000 times more brightness than the full moon. That's really bright. That's going to damage your eyes. So you need to be careful with these eclipses. Likewise with the partial eclipses. Actually, even at 99% eclipsed, and I'm going to come back to this later, even at 99% eclipsed, you still have something that is 10,000 times brighter than the full moon. So you have to be really careful. Okay, why do we get different types of eclipses? Well, I'm going to introduce you to something that some of you will already know, and some of you will be like, what? Wait, what? Okay, this is an exaggerated diagram, but basically what I'm showing you here is the moon's orbit around the Earth. The moon's orbit is not exactly circular. It is slightly oval or elliptical. It's elongated. It's about, the moon is going to be about 10% closest at its closest point. We call this perigee. It just means closest to Earth. Then at its furthest point, apogee means furthest from Earth. So it's about 10% closer. Now, you know that if you have something closer to you, it looks bigger. And if it's further away from you, it looks smaller. Closer to you looks bigger. Further away from you looks smaller. And so you have the same thing with the moon. The moon is not actually changing size, but when it's closer to us, it's 10% closer. So it looks 10% bigger. When it's at the other end of the orbit, it is 10% smaller. It's going to look 10% smaller because it's 10% further away. And what that means is that sometimes it can block out the sun completely, and sometimes it's just not big enough. Okay, but actually, let me just digress for a second. So if any of you have ever heard of the supermoon, most people have, the supermoon is basically when the moon is at its closest point and a full moon at the same time. Remember that it's only, when it's at full moon is not going to be at the same place on its orbit every single time around because of the Earth going around the sun. And so it's only going to be at this point and a full moon about once a year. So the supermoon is basically the biggest appearing full moon of the year. And you're also going to have a smallest full moon of the year 6 months later. Okay, now I want to mess with your heads a little bit more. Here I've brought together, here's the sun, here's the Earth going around the sun, here's the moon going around the Earth. Okay, so again, we've got those terms perigee for closest to the Earth, apogee for furthest to the Earth, and then the same terms for going around the sun, perihelion, helion is sun, so it's closest to the sun, furthest from the sun. We are actually closest to the sun in January and furthest from the sun in July. So what that means is that, whether we get an eclipse that is total versus one where you can still see the edge of the sun really depends on not just where the moon is in its orbit, but where we are in our orbit. So you can see here, you can imagine that at perigee, the moon is quite big, but also at perihelion, the sun is quite big. And so we may still not get, I will actually show you the answer in a second, we may not quite get a total eclipse. Let's have a look at how they actually match up. So here what I'm showing you is we've got the moon and its apparent size and basically the difference. Remember I said it's 10% smaller at its furthest point than at its biggest point, closest point. And so you can see the apparent size change. And likewise for the sun, but our orbit is more circular. It's not quite as stretched out. And so what you see is the sun's change in size is much less dramatic. It's only about 3 or 4% difference between its smaller size and its biggest size. The important thing here is that at its biggest size, the moon can block out the sun even when the sun is at its biggest size. But at its smallest size, the moon cannot block out the sun even at its smallest size. So again, you need to think about where are we in our orbit, where is the moon in its orbit, and those two put together will determine whether we see the edge of the sun as seen in the diagram up to the right, or whether we get to see the amazingness of a total solar eclipse. Okay, so this map is showing you all of the eclipses, both total and annular, where you will see them from. So this is not the partial eclipses that you see along the way. This is the seeing the total and annular eclipses. The blue lines are the total eclipses. The red lines are the annular eclipses. You'll see that there is a red line going into the US. That is the May 2012 eclipse that we saw a picture of from earlier. That was an annular eclipse. I drove my kids from Missouri to New Mexico for that one. And then we can see going all the way across the US, the 2017 total solar eclipse. But like the other one that we were looking at, that was just total eclipses and globes, you'll notice that in a 20-year period, most of the planet doesn't get to see either type of eclipse, whether it's an annular or a total. Most of the planet doesn't get to see one. Let's also look at the next 20 years. So this is from 2021 to 2040. So this includes last year. And obviously, the most important thing for us right now is that X marks the spot right over South Texas. So you can see that there is an annular eclipse in red that is going from northwest to southeast. And then there is a total eclipse in blue going from southwest to northeast. And that's the stuff that we're going to focus on from here on in. But before we go there, I would like to talk about how long eclipses last, because that is a complicated issue. So here I've got an image of the sun, and the Earth is going around it. And you'll see that it's showing it as elongated. We already talked about how the Earth's orbit is not a circle, it is an ellipse. What happens is that as it comes in close to the sun, it is moving faster. And as we move further away from the sun, it is moving slower. And so what we get is it's going to move fastest, closest in, and slowest, furthest out. This is actually true for anything orbiting anything. And the more elongated the path, the orbit, the more difference there is between the slow part and the fast part. So for instance, comets have really, really elongated orbits. They orbit the sun, but they do it in a way that's really, really stretched out. So they move really fast around the sun and then really slowly out at the other end, out past Pluto. The important thing to understand here is that this is happening for the Earth. So we are actually moving fastest around the sun in January and slowest in July, which may explain the endlessness of South Texas summer. At the same time, you're going to have the moon doing the same thing. Remember, the moon's orbit is slightly more stretched out than the Earth's. And so it is going to be moving slowest when it's closest to the Earth fastest when it's closest to the Earth and slowest when it's furthest away. So again, just those two things mean that depending on how fast we are moving around the sun, how fast the moon is moving around the Earth, that will dictate how fast things are going. There is also an effect that comes from latitude that I'm not going to get into here, but the ground that you stand on Earth doesn't move at the same speed at different latitudes. So that also has an effect. There's one more effect that we have to worry about. And I'm going to need to click on the slide. Give me a second. So I want you to see here, we've got a circular shadow, and that shadow is moving along the ground. And if you're in the middle of the path it is moving along, that is the position 2, you will be under that shadow for longer. If you're at point 1, you're not going to be under the shadow for quite as long because of the shape of the shadow. And as you get to the edge of the path of motion, it is going to be very little time at all. So again, you've got this other factor. If you're at the middle of the path of totality or path of annularity, you will get longer time in the eclipse. And if you are at the edges, you will get a much shorter time. Okay, so now I'm going to talk about the actual eclipses that are coming in 18 months and 2 years, respectively. We have an annular eclipse in 2023 and a total eclipse in 2024. And this is just a close-up, again, on South Texas, and not just because I live here, although that helps. What I want to point out here is this is where the two cross. And so I'm going to focus in on this area just because I can't talk about everywhere along the path in detail, but I will talk about the whole path as we go along. And for the record, I live in San Antonio, yeah. So I will actually get to see the eclipse from my house because I live northwest of central San Antonio. So I will actually get to see it. Okay, so let's talk about the annular eclipse first. What we're going to see next is this is a plot of the entire area that is affected by the eclipse. So this whole area that you can see, we've got the whole globe, the darker blue area, all of that area is going to see a partial eclipse. If you want to actually see the annulus, that is, you want to see the ring of fire, you want to see the moon move right in between, and so you can see the whole ring of the sun, you have to be on the yellow path down the middle. You can see there's still quite a big area that's going to get to see it, but you have to be on this yellow path. Everywhere else just gets to see a partial. Okay. Let's zoom in a little bit and see this in a little bit more detail. And this will also give you an idea of how much of a partial. So again, here I've got the path of the eclipse. Now, the other thing I want you to notice is the shape of the shadow is going to change. You can think of this as being just like, when the sun is low on the sky, you're going to get long shadows, and when the sun is high in the sky, you're going to get short shadows. It's a little bit like that. It's the angle that the shadow is coming in at. So it's very elongated when it hits the coast of California, Oregon, and it gets more and more circular as you get down into Mexico and South America, and then gets more elongated again. And that's true for all eclipses. It's going to go from elongated to more circular to more elongated. The other thing that I want you to notice is if you look on the right-hand side of the view graph, it shows you the partial eclipse that you get. So it's showing you what sort of eclipse you get. So if we look at Dallas, for instance, for this annular eclipse, Seattle and Denver and Dallas are all basically on this line that is 80%. And so they're going to get an 80% eclipse. That's not bad. It's not as cool as the annular eclipse, but it's pretty cool. An 80% eclipse. So you're starting to notice the change in brightness. The animals might actually start doing stuff. As you get up to, say, Washington, D.C., though, now you're only down at 30% eclipse. And so nobody's going to notice unless they're actually using something to view the eclipse safely. Likewise, if we go to the other, to the south side of the main path, you can see that, Los Angeles is getting 70% eclipse. And so, all of these places are going to get to see, and basically the whole of the US is going to get to see a solar eclipse, but the only places that will see the annularity, that is the ring, is on this narrow path down going from northwest to southeast. Let's zoom in a little closer, and I've deliberately zoomed in a long way. This isn't showing the whole of the path, this is showing the path close to where I live. You can see San Antonio on the map. This is actually comes from this website here. Actually, if you just go to Jubia, it's actually Xavier Jubier. It is his website. He built this using Google Maps, and it allows you to put in your own address, find out what it's going to be like where you are. And so you can just put in that first part, and then you can probably find your way through it to find this map. Anyway, what you can do is you can put in your address, you can just zoom in, anything you would do with Google Maps, you can do. In this case, I actually put in my address. And what it's showing you is when I click on my address, it gives me all sorts of information. So this table up in the upper right is giving me all sorts of information. It's telling me, first of all, how much time I get. So that's right at the top of that box above the little blue square. It says basically I get 4 minutes of annular eclipse. If we look at the table down below, it tells me when it happens. It's in UT, which is basically the same as GMT for people who aren't used to universal time. It is basically the same as GMT. Now, there is a question as to whether we will still do daylight savings or whether we will only do daylight savings. But let's just pretend that it's just going to be like it is now. It will be daylight savings in October next year, and that means that the Midwest and the central zone, which is where San Antonio is going to be mostly at the -5 hours. So we have to subtract 5 hours from this. So what that tells you is that the eclipse starts at 10:23 a.m. local time. It will become an annulus. You will actually see the proper annular eclipse at 11:51 a.m. and will end at 11:55 a.m. and then it'll be partial again until another couple of hours later, hour and a half later. And so I can see exactly what time I need to be paying attention. I can also tell how high the sun is going to be. This column that says altitude, that's how high above the ground it is. You can think of it as being, if I'm looking at the horizon, that's 0 degrees. If I'm looking directly above my head, that is 90 degrees. So actually it's about halfway up for this eclipse. It also tells me what direction to look in. That's the ASI. So this is lots and lots of useful information. You can click on anywhere and it will tell you exactly what to expect, even if you're not on the path of totality and annularity. And if you're not in this shaded area that you can see here, you will not see the annularity. You'll not see an annular eclipse, but you'll still get a good partial, and it will tell you exactly how good and when, what direction to look in if you click on your location. If you are within this path, you will get to see something that looks like that little inset image to the bottom left. Okay. Now, we talked a little bit about timing and how long eclipses last. If you've got a really big screen, you may just about be able to see this. The resolution should be good enough. But if you can't, this is from the greatamericaneclipse.com, and it shows you the timings. And so you can see here, as you look at the edge, you're only going to get a few seconds of annular eclipse. And as you move across to the middle, you're going to get a lot more time. It's actually almost 5 minutes at the longest duration, and then it will drop off again as you move to the other side. So where I live in San Antonio, we actually get about four minutes. Okay, so that's the annular eclipse, which is cool, but nowhere near as cool as the total eclipse. Remember all those things I said you're going to see and feel and hear, and it's going to be amazing. So this is that same sort of view graph as we saw before. We've got the globe. This darker blue area is where sees a partial eclipse. You'll notice that basically the whole of Canada, the whole of the US, except for Alaska, because here's Hawaii, it's in the partial phase, the whole of Central America and the Caribbean, they're all getting a partial eclipse. In fact, even you look closely, you can see the Western British Isles gets to see a partial eclipse. But if you want to see totality, you have to be on this yellow line, and that's where you're going to get to see the whole thing. And so that's where you want to aim to be. Let's take a close-up on that. Okay, so here I have the path again, and here it's showing you those partial eclipses. So you can see that the whole of the US gets a partial eclipse, but as you get up to, say, Seattle, you're getting only around less than 20% eclipse. But if you're on this path, you're getting a full-on total eclipse. Okay. So this again, I took a close-up close to where I live, mostly because then it's easy for me to interpret. But this is that same website, and you can go and look and see where the path of totality is. If you are not between these red lines in the dark shaded area, you are not going to get to see the whole thing. I want to reiterate that 99% eclipse is not 99% of the experience. In fact, even at 99.9% eclipse, that's still 0.1%. That's 1,000th of the sun still showing. If there's 1,000th of the sun still showing, it's still 1,000 times brighter than the full moon. That's too bright for you to see the corona. You're going to feel some of the other stuff, but you're not going to see the corona if it's even at 99.9%. So you really want to get into that area that is 100% eclipsed. And again, you can click on it and find out what time. Again, it's in UT. So for my location, the total eclipse actually starts at local time. That's going to be 1:32 p.m., 1:33 p.m., and finish at 1:35. I actually get just under 3 minutes, about 2 minutes 45 at my location. But my location is not in the center. If you're close to the center line, you're actually going to get much more time in the eclipse. And we'll look at that in our next slide. So here you can see, again, this is showing you the contours with the timing. Again, I'm showing South Texas and Mexico, in part because Mexico actually gets the longest duration. If you're in the middle of Mexico, you're going to get about 4.5 minutes. Actually, you get almost that in South Texas if you're on the center line. But if you're at the edges, you don't get anywhere near that much. And so you want to be as close to the middle of the path as possible and as far down towards that point in Mexico as possible to get the longest duration. Now, there's another consideration, which is, ooh, that's weird. There's another consideration, which is to do with how the weather is going to behave. And this view graph hasn't quite come out right. I think there's something weird with the green screen. But basically what this is showing is expected cloud cover. And I can talk through it because I know what it looks like. Basically, you can see here there's the path of totality and some various different locations on it. And what's been done is they've taken the cloud coverage for the US for the time 1800 UTC. So again, that's about the same time as the eclipse will cross the Mexico-US border. But they've done that for 5 days either side of the day in the future that's going to happen. So from April 3rd to April 13th, since the eclipse is on April 8th. And they've done it for the years 1979 to 2016. So this is taking an average of all of that cloud cover, trying to get a feel for what should we expect in cloud cover for this time. And what we find is that the highest chance of cloud cover is the furthest north on the path. So if you're up in Canada or up in New York or even parts of Ohio, you're actually up at 60 to 70% chance of cloud cover. Remember, this is chance of cloud cover. This doesn't say it's really going to happen. As you move further down, as you get to Indianapolis, it's more like 50 to 60%. As you move down into Arkansas, it's at 40 to 50%. Northern Texas is also that level. As you get to South Texas and into northern Mexico, it's at 30 to 40%. And then further south into Mexico, 20 to 30%. So I'm sorry this didn't show up on the view graph very well, but the point is that you have less cloud cover in Mexico and South Texas, and as you move further up the path, you have more and more cloud cover as a probability. Now, having said that, I was in Missouri for the 2017 eclipse, and we were predicted to have about 50% chance of cloud cover. And in fact, most people in Missouri got to see it. Not everyone. Some people were rained out, some people had cloud cover, but it doesn't mean you won't see it at a given location, but it does mean your best chances of not having cloud are the further south down the path you go. All right, so let's just kind of bring a couple of things together and talk about how much time we have left before these things are happening. And then I want to talk a little bit about safety. And so what we have is the annular eclipse is happening in 18 months. In fact, it's happening in exactly 554 days from today. The total eclipse is happening in 731 days. That is 2 years exactly. So we have an annular eclipse on October 14th next year, and then the total eclipse in 2 years exactly. And so we need to get ready for that. And there's a few things that we need to do in preparation. The most important thing that we need to worry about is eye safety. Okay, so please don't point binoculars at the sun, at least not unless it's totally eclipsed. Remember, I said you can use binoculars to look at the total eclipse, but even if it's slightly showing, do not point binoculars at the sun. It will destroy things. What you need is, I already mentioned this, these special glasses. Remember, I said that even at 99.9% eclipsed, you've still got 0.1% of the sun showing, and that's still 1,000 times brighter than the full moon. You have to wear these things until it's totally eclipsed. You can see here that we call them solar viewers because it doesn't have to be an eclipse. You can use them anytime. We used the same sort of glasses to watch the transit of Venus when Venus moved in front of the sun back in 2012. We used the same types of glasses to look at a really big sunspot that you could see without a telescope. So you can use them any day, but if you want to stare at the sun, you absolutely need to use something like this, or you need to be doing those projection things that we talked about before, like using a colander or something with a little hole in it. This is kind of what it looks like. This is a little misleading. I don't know if you can see. It looks like you can see clouds. The only thing you can see is the sun. In fact, little kids, when they put it on, they'll go, moon, because this is what they think. It looks like the moon because it's about that brightness. It's not, it's cutting out. Basically, only a millionth of the light gets through. And so it's only about as bright as looking at the full moon. And so you see this crescent and it is completely safe. You can also get your glasses branded. You'll see here, I have a nice UTSA Rowdy Roadrunner on my glasses. But hopefully there will be lots of these around for those of you that want to see this. And for those of you who will see partial eclipses, or those of you going to an annular eclipse, you have to wear these all the time to look at the sun. It is never safe to look at the sun without them during those eclipses. I want to mention briefly a little bit about just some traffic things that you might want to think about. So here I've got some law enforcement enjoying the eclipse. And here some people came prepared with, chairs and things to chill out and watch the eclipse. But you can also see that there's some traffic. And this is something that we do need to worry about. In fact, what happens is, and we'll take a look at the next slide, you'll actually see that although it's showing you two images from Wyoming, one is the Tetons before the eclipse and one is Wyoming after the eclipse. But the Tetons is always busy in August. And actually people will come to wherever they're going to visit to see an eclipse over several days. It won't be something that they just show up for all of a sudden. It'll be something that they are getting there over a few days and not all at once. But as soon as the eclipse is over, everybody leaves. So that post-eclipse in Wyoming, that's all the people who had gone to try and see it somewhere in Wyoming and then wanted to leave instantly. And now they're all blocking the highways. In fact, what you're seeing on the map is you can see all of those lovely green, mostly interstates that are nice and clear. And then you can see where there's traffic problems. It's in orange and then in red if it's really bad. You can actually trace where the 2017 eclipse went just by looking at this. And this is showing you where the traffic was right after the eclipse as people are trying to get away from wherever they were watching it. So it is something that we have to pay attention to. And you want to make sure that you think about this in terms of where you're going to go and watch an eclipse and maybe hang out for a bit longer and enjoy the place. Come to San Antonio, it's cool or hot. I'm going to finish by leaving you with this wonderful cartoon from the XKCD. And so what this graph shows you is, the horizontal axis says how cool it sounds like it would be, and the vertical axis is how cool it really is. How cool is it to really see it? And so you can see there's planetary conjunction. Yeah, unless you're actually a diehard astronomer, don't even bother. Supermoon, you won't notice the difference, but by all means, go and look at it. Lunar eclipse, that's pretty cool. It's pretty cool to see a lunar eclipse, but you're more likely to have seen one. No, partial eclipse is cool. It is. And so is an annular eclipse, which I would put probably somewhere up here. But the total eclipse is off the chart. They can't even plot it on here. It is so completely different to any of those others. If people tell you that they saw the eclipse and were underwhelmed, it means they only saw a partial, because nobody sees a total solar eclipse and is underwhelmed. It is an amazing thing. And you can find out all sorts of interesting information from our official American Astronomical Society website at eclipse.aas.org. And I look forward to seeing you all in totality. And now I'll take questions. Well, okay. So basically, hopefully you have got some idea of what to expect and have excited about the idea of seeing any of these types of eclipses, but especially the total eclipse. And you have an idea of where you might be able to go and see it and what your best chances of having the longest duration are. And also know how to safely view an eclipse. And I really look forward to seeing as many people as possible in totality in 2 years from today. Thanks, everybody.